Hello, good day. I'm Teacher Renzo, and today we will discuss about the work and energy. But before that, I just want to welcome you in our asynchronous day. Today, let's watch the short video that teachers of Professor Dave prepared for you for to introduce what is work and what is energy.
Professor Dave here. Let's learn about work and energy.
He knows a lot about the science stuff. Professor Dave explains.
Just like force, the words work and energy have a variety of connotations in common language. When we say work, sometimes we mean exercise. Other times we mean a place we go every day and do something to earn money. Energy is even more convoluted. We might say that today we have no energy, meaning we feel tired. Or we might use the term in a completely metaphorical way, saying that a person or a location has good energy. But once again, in physics, these words mean something very specific, and if we are to learn science, we must allow the rigorous definitions to replace the colloquial connotations. Work is defined as action done on an object whereby an applied force causes a displacement of that object. A basic example would involve pushing a box 10 meters across the floor. Work is equal to the magnitude of the applied force times the displacement of the object. So it has units of force times distance. If you push with a constant force of 100 newtons over the 10-meter distance, you would do 1,000 newton meters of work, which are equivalent to another SI unit called joules. This means that work can only be done when displacement occurs. If you push a brick wall with the same force for the same amount of time as the box, you may get very tired, but technically you have done zero work. In addition, only the components of the applied force that are parallel to the displacement are considered to be contributing to work. If you push the box with your arms parallel to the floor, all of your effort contributes to work done on the box. But if you are pushing at a downward angle, only the x component contributes to work, while the y component does not. In such a scenario, instead of using W equals Fd, we could calculate the work done on the box using W equals Fd cosine theta, as this will give us the portion of the applied force that is operating in the horizontal direction. If theta is 0, meaning the applied force is horizontal, cosine theta will be equal to 1, leaving us with W equals Fd. And if you were to push straight down on the box, theta will be 90 and cosine theta will be 0, meaning no work is done on the box and it will not move. Any angle in between and there will be some motion. We must bear in mind that work is a scalar and it can be positive or negative. Work will have a positive value when the applied force is in the same direction as the object's motion, like when pushing the box. And work will have a negative value if the applied force is in the direction opposite the object's motion, like if your baby brother pushes the box the other way, but without enough force to stop it from moving forward. The sign on work is very important because it tells us if the speed of an object will increase or decrease as a result of applying the work. Energy, another elusive term, is quite simply the capacity to do work, and this is summarized in the work-energy theorem. This states that when work is done on an object, there will be a change in that object's kinetic energy, which is the energy of motion. This also means that an object in motion is able to do work on another object. The work-energy theorem brings together concepts from Newton's laws and kinematics to describe motion in a way that we will examine further in the next clip. For now, we must simply purge ourselves of any prior connotations of the word energy and understand that it merely describes a property of an object or system that can be transferred into another object or system, often in the form of work. There are different kinds of energy, including kinetic and potential energies, thermal energy, chemical energy, and more. And we will discuss all of these when the time comes. Once again, the SI unit for energy is the joule, which is defined as a Newton meter, even though energy is not always transferred in the form of work. But our understanding of energy will grow as we examine the various types of energy. So let's move on to that part of the course.
Okay, that is energy and work or work and energy. Now, let us let us define what is work and what is energy. Okay, work and energy. So when we say work, is energy transferred to or from an object via the application of force along the displacement. In its simplest form, it is open, represented as the product of the force and displacement. Then again, energy in physics, the capacity for doing work or the capacity to do work. It may exist in potential kinetic, thermal, electrical, chemical, nuclear, or other various forms. There are moreover heat and work, example, energy in the process of transfer from one body to another. After it has been transferred, energy is always designated according to its nature. Hence, heat transferred may become thermal energy, while work then may manifest itself in the form of mechanical energy. Now, again, the formula in getting the result or the product of work is work can be calculated with the equation or work force times distance. Thus, a unit for work is joule or newton, meter, newton, or newton meter. 1 joule equals the amount of work that is done when 1 newton of force moves an object over a distance of 1 meter. And for energy, the formula that links energy and power is energy is equal to the power multiplied by the time. The unit of energy is the joule. It's the same as the work. The unit of power is watts. And the unit of time is the second. So that's it for this time. Thank you, and you can now proceed to your activity on your activity folder in Edmodo. That's it. God bless you. I hope you learn. Thank you.